So I'm going to do a quick recap, start with a quick recap of what we were talking about previously. Remember, this entire chapter is about bilinear forms. This entire chapter is about bilinear forms. And occasionally sesquilinear forms, but all that good stuff. And one of the big takeaways, I think, from Duhan's lecture last week is that there's this procedure, um, and sorry, yeah, let me sorry do a little thing. This is the notation that I'll use, so like v comma w in those angle brackets, so analogous to the inner product, and um, all of my forms, all my vector spaces today are real vector spaces. So, like that. Just let me give myself just a little bit more space here. Okay, so, sorry, to finish the sentence that I started, um, uh, the main takeaway, I think, from Duhan's lecture is that uh, it is possible to represent a bilinear form using a matrix. Um, and just to have some notation, I'll call this M. And doing so requires sort of a cost, which is that you need to choose a basis. I'll denote my bases with these fancy B's. So this is not too terribly difficult to do. We need the we can be very precise about what this means. So if I tell you how a bilinear form acts on every pair of vectors, then I have told you the bilinear form. And we can do that by saying what we want to do is something like multiply, sort of stick the matrix in the middle of these two vectors. But this doesn't quite make sense because even if these were like column vectors, this first one would need to be transposed. Remember, this here is a real number, so the thing that we get had better be a 1 by 1 matrix. Um, Federico, I hear you. Thank you so much. But still, this doesn't quite make sense because these things, these v and w, are elements of the vector space. Matrix, so they're not necessarily even column vectors, but they can become column vectors, right? This is the purpose of the basis, is that if you write out their coordinates, then the matrix tells you what to do with those coordinates. Cool. One of the early theorems from the lecture was that if your form is symmetric, then that means that your matrix, the resulting matrix, is symmetric. Almost everything we talk about today is going to be related to symmetric forms, or maybe I should say the first half for sure is going to be related to symmetric forms, and probably most of it as well. So this is a useful thing to keep in mind, that symmetric bilinear forms produce symmetric matrices and vice versa. A couple of classic examples. So our favoritist example ever is the one for which the notation, we're stealing the notation from, the dot product. So the dot product on Rn. And if we follow this procedure with the standard basis, then what happened here is that the n w1, and that's what those things would look like, what two generic vectors would look like. And so in order to get the form, the form that we want is v1 w1 plus v2 w2 plus vn wn. And so to get those, this v1 to match up to that w1, we're going to need a 1 in this top left entry, and zeros everywhere else. And it's not too hard to convince yourself that what you need here is precisely the identity matrix. So this is a fairly tame example in a lot of ways. We've talked a lot about the dot product, or at least a lot about inner products and Hermitian forms as we've later in the earlier lectures. But for more sort of exotic or perhaps more indicative examples of the things that we're going to talk about today, I would encourage you to keep the following example in mind. Uh, I'll just be super concrete about it. So in R3, we can consider what does it mean to take v1, v2, v3 with w1, w2, w3. I have to give you some formula. And make this one. So it completely ignores the z coordinate. And it's kind of like a dot product, except that on the other two coordinates, except that it has this minus sign. So here, again, using the standard basis, the matrix would be 1, minus 1, 0, and zeros. It's worth convincing yourself that this matrix does indeed correspond, right? If checking that is a good sort of first check to make sure that you understand what this blue arrow is doing. And hello, Apocalypse. So that I would argue was like the main, maybe the first half of the lecture last week, and the second half of the lecture last week was concerning this idea, very common idea in linear algebra, is you say, well, okay, we've got this object and we can represent it in some way by picking a basis. Well, what if I pick a different basis? And I have some change of basis matrix P that turns one basis into the other. Well, we're still going to get some matrix. I'm just going to call it M twiddle, and my M twiddle is exactly Artin's M prime. I just think the twiddle is a little bit more easily readable. And so this big result was what Artin calls corollary 1.13, uh, was argued last week, is that, and I got to get this right, this is a little subtle, um, that the relationship between these two matrices is as follows. Um, so if anyone knows this stuff really well, you can try to critique this, but I think this is actually correct. So what is definitely true is that there's some matrix here, transpose, and some matrix here. I believe that that matrix is precisely this P, but it could be P inverse. I spent a lot of time thinking about this last night, and this was the conclusion I came to, but I always get these binary things wrong. So highlight this. Okay, what are we doing today? So today, I want to take this blue arrow, and I want to sort of observe that in these two examples that we had here. Let's start there. Let's start with these examples. In these two examples, we ended up having diagonal matrices. Right? Now, we were using the standard basis, we were using really nice forms, so it's perhaps not super surprising that the matrices would also be nice. But in particular, the thing I want to emphasize is that the forms, these bases are sort of adapted to these forms in some sense, right? And the standard basis is very special in the sense that it's an orthonormal basis. And you might suspect that perhaps if we focus our attention to orthonormal bases, then the matrices that we get might also be special. Now, this is a little bit tricky to do because, well, orthonormal is a concept that makes sense in the context of an inner product. And here we don't necessarily have an inner product. The only thing I've told you is that we have a real vector space. But let's pretend for a second that um, this concept does make sense. So can we choose an orthonormal basis? Or some particularly nice bases? Goofy, this is a lecture about the about chapter 7, specifically section 7.2, and probably some other stuff from Artin's abstract algebra book. You can find more information in the text chat. Max, I'm not quite sure what you're saying. Let me just make sure that what I'm expecting to show up on screen is showing up on screen. Okay, yeah. Okay, so for an orthonormal basis, right, if it really were a an inner product, we would expect to get the identity matrix. I have an echo. Fascinating. Um, yeah. Okay, if other people have this concern, I'll try to do some technical lookup at the break, but I think we're probably gonna leave it at least for now. So we have this identity matrix, right? Um, uh, that's what an orthonormal basis would look like for an actual inner product. It would just be the identity all the way down. However, since um we have this purple example from before that I want to remind you about, we know that we couldn't possibly hope for the identity matrix because you're allowed to do weird funky things like just ignore some coordinates, right? You're allowed to do weird funky things like, oh, you can uh, think about some vectors as being like negative vectors, right? Having negative lengths. But perhaps you could hope that you would get like an identity for a little bit, and then maybe a negative identity for a little bit, and then maybe some zeros. Uh, I'm gonna be slightly more agnostic about how long these dots are, or excuse me, these pieces are. Um, and just to have some terminology here, or to some notation, I'm going to say that maybe our basis, for some basis, we have like some number of things, some number of, I'm going to call these like positive vectors, right? Vectors whose form with themselves is positive. And then these are negative vectors. I'm going to use n for the dimension of the vector space, so I have to pick a different, I can't use n, sadly. Um, but Artin uses m, I think that's a good choice. And then zeros, so some number of vectors which are self-orthogonal, a concept that Duhan was talking about at the end of last week's stream. So currently, I'm not, this is kind of a pipe dream, right? If for this example in particular, we know that such a basis exists. It's the standard basis. But I mean, you can reasonably ask the question: Is do these things exist? Uh, Something that would give us a nice diagonal form like this, or excuse me, would turn the form into a matrix that was nice and diagonal like this. And then you could ask questions like, are they unique, right? Is once you ask existence questions, you always want to start asking uniqueness questions. And your intuition should probably be like, yeah, probably not. Like orthonormal bases are like very non-unique in the inner product setting. It doesn't feel like things should improve over here, and so we can start to ask sort of the same question again. We have this basis over to the left. What if you have excuse me, have this basis over to the right? We have a new basis over to the left. What is the relationship here? So we have different shade of green. I think that's a different shade of green. Okay. And so what it means to be an orthonormal basis is, of course, that you have like so you have the identity for a while, and you have minus the identity for a while, and then you have the zero matrix for a while. Um, but one thing that's even sort of not obvious here is like, okay, yeah, are we sure? How confident are you that these two forms right here, these two forms are even different forms, right? It kind of feels like they should be. Um, like you shouldn't be able to convert a positive one to to a minus one. Um, but it's not so clear. So in principle, by choosing a different orthonormal basis, you could get oh, different sizes of blocks here. Goofy, yeah, sorry, you might not have been here for this. The best way to get your questions addressed is to type them in the text chat. If you make it a sincere effort and I can't figure out what you're talking about, then I'm happy to try to have you explain. But so here is the main content of the section, or yeah, this section, I would say. So it's a theorem in two parts, an existence and uniqueness theorem. So the first is that orthonormal basis, whatever this means, exist. And when I say they exist, I mean for all symmetric are bilinear forms. Maybe I should say something about finite dimensionality of the vector space. Not entirely certain. Not entirely certain, but I think that's what is at least the generality that's proved in Artin, that his vector space throughout this chapter or this section, and I think throughout the chapter for the most part, are finite dimensional. Yeah, and this theorem, ooh, I think the proof of this theorem that Artin gives might be problematic in the infinite dimensional setting, but I'm not going to say too much more about that. At least without axiom of choice. Although I guess that's not saying too much. You have to have axiom of choice even to have a basis. So in addition to the existence, and the signature of the resulting matrix does not depend on the basis. So when I say the signature here, I'm talking about, and maybe to really emphasize this, I'll put this in green. I'm talking about this PMZ, or you can just abbreviate it to just the P and the M. What's the structure of an orthogonal matrix in the context of this lecture? Yeah, so I haven't defined an orthonormal basis, and I will do that. I'll define both an orthonormal basis and a signature, but for now I just sort of want to give you the flavor of these things. But essentially, it's a matrix precisely adapted so that these so that you get this diagonal form, or this diagonal structure for your form. Nice, nice. Of these two theorems, this second one is usually considered the more significant one. So this has a fancy name. This is called Sylvester's. So Artin just calls it Sylvester's law. You'll also find it, for instance, on Wikipedia called Sylvester's law of inertia. And I cannot explain to you what this word is doing in this context. It's definitely something physicsy. So some of you noted that there's these forms that we were producing that kind of looked like dot products from before, but with minus signs, do have this kind of like Minkowski space-time field to it. That's literally all that I know how to say. I don't know what that means. I don't really know how that's related to physics, but I am guessing that that's sort of the connection here. But yeah. When I say signature in this theorem, really what I mean is I mean these three numbers. How many positive vectors there are in your basis, how many negative vectors there are in your basis, and how many zero vectors there are in your base. They're self-orthogonal. Of course, since we're fixing the vector space V, Z is determined by P and M. So oftentimes the signature is just P and M. So let me maybe emphasize that. That's unreadable. Let's try that again. Yeah, it's a good question. So these are our goals for today. Cool. Oh, so maybe Transient says uh, this is another name for the signature. So maybe that's where that terminology is coming from. Yeah. Cool, cool, cool. So just so I want to go and prove these theorems, but I will say um there's one piece of these theorems that I think is going to be the most important for me, just because like reading it in the textbook is obnoxious. But it's not actually that difficult of an idea. It's just like hard to read. The others, if if we run out of time, I can't talk about them. That's fine. I think the text is pretty readable on that front. But there's one that I'd like to sort of lead you through by the nose, because it's just easier to understand that way. And that's going to be sort of the second half, in some sense, of this law of inertia. But just to be complete, before we start getting into those proofs and start to think about other things, let me just finish stating the theorems by writing down definitions, right? Um, so, so what actually is an orthonormal basis? Thank you for asking that question, Goofy. So for a real vector space, V uh, with a symmetric bilinear form. A basis of V is orthonormal. Um, and if I need to clarify, I'll say it's orthonormal for this form. If it satisfies two conditions, just like in the inner product case, we're going to want like an orthogonality condition and a normality condition. So the orthogonality condition is the one that probably makes the most sense, right? It's that if you have two different indices, I should maybe name this basis. Um, so if you have two different basis vectors, then the form of one with the other is 0. Seems reasonable to call that orthogonality. In fact, Artin defines orthogonality, does not define orthonormality. So that's a Ian Stuckey special, but I think is a reasonable extension. Since we're going to be talking about these quite a bit. Yeah, exactly. So what does normality mean in this context? Um, so again, it should have something to do with what happens when you take the form with itself. Ordinarily, it would mean that it's positive 1, but we know from that purple example that we can't hope for something that good. So we have to allow positive or negative ones or even zeros. This is, in this context, this is what we mean by a normal form, or excuse me, a normal basis. It is worth noting that there's no essential difference, just like in the inner product case, there's no essential difference between having an orthogonal basis versus having an orthonormal basis. Um, um, and you might say, well, this doesn't even really need to be said because it's like exactly the same as the inner product case. Well, it's not quite. Remember the difficult or the trick there is that you could divide things by uh, the norm or the square root of the norm. The problem here is that because the reason why that worked is because you always knew that this thing was positive, right? And so this would be a real number. Um, but in our case, we don't know this. So we have to perhaps flip the sign. So make it so that the thing under the square root is a positive number. Or it could be 0, and you can't divide by 0. Um, but the good news is that if it's non-zero, excuse me, if it's already orthogonal, then you're already normal, right? So you didn't have to worry about that. Yeah, so Goofy, in uh, this is by normality, I mean the second bullet point here. And this is supposed to be an analogy to like the usual sort of like calculus notion of a normal vector, right? It's a vector that has length 1, except in this case, because our forms are a little bit weird, we have to allow these other possibilities. By the way, this sort of trick here also explains why this -1 is like doing anything for us, because even after you fix this problem and you fix this sign problem and you make it say like, okay, we'll just take the negative uh, length square instead of the positive length square. Um, well, that is still guaranteed to get you a positive real number. And so, so that can't change the sign of this form. It can't change the sign of this form to be +1 instead. The other thing that I suppose I should define for you is this concept. And sorry, this might freak the scream out a little bit. Um, but hopefully things should be back. Um, uh, what was I going to say? Is this notion of a signature? Is that what I want to do? Nah, I'm actually going to save that. I'm going to save that to when we write the proof down. Okay. Um, so I think let's call this a quick break. It's not been a full hour, but we might take 2 breaks today. We'll give it 5 minutes, I guess 4 minutes. We'll come back at quarter till. Hello, folks. Welcome back. I see there was some chatter in the chat. Thank you, Tracy. Um, excellent. Yes, and just to follow up on that comment, Artin defines orthogonal bases for symmetric forms, but yeah, I'm just because we're going to be talking about for, this stuff for Sylvester's law, I think it's just a little easier to have this extra piece of notation. Um, So we can have some notes for later, but references, nope, I remember doing this before. I know you can select everything. You can delete everything. Goodbye. Excellent. And we'll get back to it. So let me begin by defining, or the second section by defining some boundaries. Sorry, I think that I caught everyone. Yeah. Always good to define your boundaries. Uh, so there were these two theorems that we had. Maybe I should have saved those. But roughly they correspond to existence and uniqueness. Um, so some boundaries. Plan. Maybe I should say logistics planning. So first of all, I'm going to skip the existence of orthonormal bases. Right. So this first theorem, I will skip proving existence for O and B. The reason why is because first of all, it's laid out entirely in Artin, although that's true of most of the things that I'm saying today. But the real reason is because morally this is just Gram-Schmidt. Um, so as usual, the fact that things are not necessarily positive, don't have necessarily positive form with themselves is going to cause some trouble. In our case, really the only issue is the self orthogonality business. The negative vectors aren't actually so bad in this context. Um, so with a minor sort of carve out, um, for self orthogonal vectors. Um, the reason why this doesn't cause yes, orthonormal bases exist for all symmetric forms, even ones which are not positive definite, even ones which are degenerate, right? So they have some null vectors. And Kaylor, I don't know if you're still here, but I'm definitely going to be addressing this issue of degenerateness. I said it wrong the last time that I was presenting, and I would like to correct that. But yeah, any symmetric form. Um, the These self-orthogonal vectors, so let me just very briefly explain why they don't matter so much for us. In Duhan's lecture, one of the things that he showed, so it's minor because Duhan showed that we can always, if this form is not the zero form, if it doesn't take zero on literally every pair of vectors, uh, then there is some non-orthogonal uh, non-self-orthogonal vector. And so the induction argument that you see in Gram-Schmidt basically just works here, except occasionally you're going to have to switch out basis vectors for other basis vectors if you happen to make some unfortunate choices and chose some self-orthogonal vectors. Mikey, I see your hand raised. If you have a question, the best way to get that answered is to try posting it in the chat. I really can't tell what you're saying. I'll try to. I'll invite you up to speak. So uniqueness is a bit subtle, right? This Sylvester's law is a bit subtle. It's why it's the more famous one, and or more celebrated, I guess I should say. And to just stated, I was a little bit imprecise when I stated it before because I was like saying like, oh, the signature is this thing, right? You know what I'm talking about. So um, just to say something, um, and be sort of precise about exactly what we're going to prove. Um, so I'm going to make up a definition. This is my definition. It's not from Artin. Um, we'll say that an orthonormal basis or a form is PM adapted. Uh, if it is, uh, well, if it's got some number of things here, one p plus m, and b plus m plus 1. The subscripts just keep getting longer. Until finally we get to bn. Where these things are 1 with themselves, these things are -1. I guess I can use different indices, why not? And I don't want to use k. 0. Okay, so the uniqueness theorem that I wrote down earlier actually says this. Sylvester's law. It says that if we have 2 bases, orthonormal bases, and I'm going to color code things here. And maybe, but I should like actually tell you what the vectors are called. I gotta give myself some more room. And let's do green. So if we have 2 bases, which I will refer to as blue and green, please tell me if you can't really tell the difference between these colors. We do have some options. But the blue vectors are the VIs, the V subscripts. The green ones are the W subscripts. Then I'm supposed to say like the signatures don't matter, right? Or the signature stays the same. So if they're if the blue basis is PM adapted, and the W basis is, or the green basis is adapted in some other way, QK. Respectively, then oops, that's not the color. Then P is equal to Q, and M is equal to K. I guess I could be really dogmatic about this color coding. Sure, why not? So So this is the statement that I'm going to prove. Except I'm not actually going to prove this either. So I said that there are sort of like two parts to this, and I'm only going to prove the second part. Let me be precise about that. So the plan, Artin's plan for this proof is step one, show that P plus M is equal to Q plus K. In other words, this piece right here, this last piece, has the same length for both of these bases, right? So these self-orthogonal, there are as many self-orthogonal vectors or as many linearly independent self-orthogonal vectors in both these bases. Now, the reason why I'm going to save that comment until after I write the second part. So that's step one, and then show that we'll show directly that P is equal to Q. Excellent. The reason why he separates it this way is because the first part, I said before that it's easy. The sense in which it's easy is that it's true not just at the level of like numbers, but at the level of subspaces. So lemma, which I think Artin actually parses out as a lemma, is that n minus p. Actually, I'm not sure that he does, but n minus p minus m is equal to the dimension of this subspace. And the point is that this thing over here doesn't care about the basis. So we're done. I mean, this lemma then implies that first part directly. So this v this v perp, this thing that I box here, seems a little bit strange, right? If you're still have your inner product hat on, but remember, because we don't have what positive definiteness anymore, there are going to be vectors that have or inner that are orthogonal to themselves, and in fact, there are going to be vectors perhaps that are orthogonal to everything. And so that is that's what this means, v perp. It means that the vectors which are orthogonal to every vector in the space. Yes, and the subspace transients, the subspace spanned by the self-orthogonal vectors is unique. That's true. I sort of said that I claimed that this was going to be at the level of subspaces, and then I didn't really follow through on that promise, right? Yeah, is there something that I could do? Yeah, I could say that it's even true that span of you know, b p plus m plus 1 through bn, so the last part of the basis, is that. So by taking dimensions on both sides, you recover the dimension result. And hello, walking stick. Welcome back. Okay. The second part is subtle in the sense that this is not true. Um, I don't have an example right off the top of my head. If someone does, because I imagine there are like well-known examples of this statement. It's not true. That the span of v1 up to vn is equal to, or sorry, not vn, my mistake, vp. So the span of the positive vectors for one basis is going to be the same as the span of the positive basis vectors for the other bases. We're going to prove that these things have the same dimension, but the subspaces are not equal. Lucas, I might be able to do that for you after the stream, but I think I'm going to need to keep going right now. Thank you for the question, though. uh, Bracket this. Okay, so we're going to show that P is equal to Q, and we're going to do that by showing that, got some, oh, that's not good. P plus n minus Q is at most n. Okay, why in the world is this enough? So first of all, just quickly doing some algebra here, can cancel the n on both sides, add q to both sides, and we get that this implies p is less than q. Less than or equal to q. And yeah, transients exactly knows what's going on here. If you know that p is less than or equal to q, then there's no reason why I colored the W basis blue and the V basis green, right? I could have switched the colors. Bases to see that Q is less than P as well. The end. So what I'm trying to do here before I called this a plan and not a proof, I'm trying to segment off all of the weirdness of like the the numerology that we're doing, right? At some point we're going to actually do some linear algebra, but right now we're just reducing it to something that is a statement that we can actually use the linear algebra to prove. What are subspaces again? Yes, they are lower dimensional vector spaces sitting inside of some fixed subspace. Sorry, sitting inside of some fixed vector space. Yes. Okay. So this is a great time for questions. We're about to do some linear algebra, but right now, so far we've just done some sort of logic manipulation tactics. Uh, so I'll say verbally, perhaps, if while folks might be typing some questions, um, that how do you prove that things are, how do you prove inequalities in the context of linear algebra? Usually this is done by showing that something is linearly independent or spans, right? Because you know that spanning sets can't be too big, or excuse me, spanning sets can't be too small, linearly independent sets can't be too big. And so that is precisely going to be the plan here. Um, proof. I'm not sure I said this explicitly, but perhaps it was clear from the way that I talked about it. I'm not going to prove part one. Um, it's the first couple of paragraphs in the Artin's proof in the book. And again, I think that it's pretty easy to read relative to this second part. That's just kind of annoying to look at. Um, I don't know. I say I'm not going to prove it. If we have time, I'll prove it. It is fun. It is a fun proof. But um, so as promised, it's enough to show that this set is linearly independent. Let me split that sentence a little bit. Okay, so which set? So we will take a purported basis, which we'll start off with the blue vectors, and we'll take all of the positive blue vectors. And then we will switch over to the green vectors, and it will take all of the non-positive green vectors. So all of the negative ones, excuse me, and not p plus 1, because to get to the positives you need q, or to get past the positives you need q. So all of the negatives and also all of the zero vectors. So why is this enough? Just to be explicit about it, uh, by taking the dimension of the span of C, well, it's a subspace, so it can't be bigger than the dimension of the entire vector space. The dimension of the entire vector space is n. And the dimension of the subspace is, well, if it's linearly independent, you just count the number of vectors there. So which is precisely what we claimed we were going to prove from earlier. So this is now our new goal. Our new goal is to show that this set is linearly independent. And hopefully it's believable now that there's actually going to be some vectors involved, right? some real linear algebra. So what does it mean to show that a set is linearly independent? Well, we have to find some linear relation, and or sorry, you have to not find one. You have to assume that one exists out there, assume nothing about the structure, and then show that in fact it could only possibly have been a trivial relation. So let's get started. Suppose that there is some Sorry, we're starting to get enough text on this page that it's not happy with my pen, but we will persist. Um, Correct. The number of elements in the set E is less than or equal to n. C, but I know you know. So, in other words, there need to exist some vector, or excuse me, some numbers, bi and c, j, r, such that, and I'm going to write out the. I'm going to follow Artin, and I'm going to write out the vectors in a sort of this linear relation in a slightly non-standard way. This is not at all a problem because to write it out in the standard way, we could just subtract sort of one half of this vector from the other, and I guess we could subtract this from both sides to get 0 over here. But it will be convenient to have these things split up. Sorry, those should be green. Whoa. Okay, got some really bad lag there. If it continues to be that bad, we'll have to have some emergency intervention, but yeah, I think P and N are not equal. Correct. Correct. I mean, well, they could be, but we're not assuming that they are. Yeah. Yeah, and that is indeed the right question. Hey, Phobos. Welcome back to stream. And sorry, I haven't quite been keeping up with Twitch chat, but it looks like not too bad. Oh, thank you, Walking, for that explanation. I don't know, Lucas, if you're still here, but much appreciated. Yes, P and Q. Yes. So call this vector. Which vector? Well, the whole reason why I set it up this way is so that I could talk about this vector, which of course is the same as this vector. V, and just to remind you that it's not an element of that basis, I'm going to put a little hat over it. And we're going to do everybody's favorite trick. At least it's your favorite trick if you are a combinatorialist. We're going to compute VV in two ways. So on one hand, using the blue expression, VV is equal to, well, it's obnoxious to write out, but let's do it. So it's going to be splitting things up linearly. We're going to get B1, B1 plus B1, B1, comma, B2, V2 plus, okay, and so on. Sure, I'll write out one more B1, comma B E B P. Okay, and then plus some other stuff, right? And then plus BN, or BP, sorry. BP, BP, BP. Okay, we can pull out the BIs, right? So let me just do that. Let me start off by pulling out these BIs. Right. By linear independence, right? So not by linear independence. What am I talking about? By linearity of the form. We can pull both of the scalars out. And the whole point, right, way back when, the important thing about this, or the basic fact about this blue basis was that it's an orthonormal basis. So v1, v2, those are two different indices. That has to be 0. Similarly, by pulling out the scalars, we get v1 and vp. Those are different indices. You get 0. And so all of these things down here are going to be zeros. Except for precisely the things on the diagonal. So the things where you have two indices that agree. VV is a bilinear form, which is just a slight generalization of a inner product for real spaces, which is what we're concerned about right now. So we get the only surviving terms are b1 squared, b1 v1 plus bp squared, bp bp. But again, not only was it orthogonal, but it was orthonormal. So this is 1. This is also 1 because we chose we stopped picking blue vectors precisely at the point when the forms went from being positive to being negative. So all of them are 1. So this is the sum of squares, right? In particular, it's bigger than 0. And as soon as I write that down, perhaps you see where this is going. But let me spell it out a little bit more. So that's one way that we can compute VV. The other way that we can compute VV is we can use the green expression. So I'll be a little bit quicker here. This is CQ1 squared WQ plus 1 WQ plus 1 plus CQ plus 1 CN WQ plus 1 W. Ooh, we're getting really sloppy. WN. And then some other stuff. And then Cn squared Bn Bn. Okay. So as before, by the fact that this is orthonormal, or excuse me, just by the fact that this is orthogonal, all of these are going to be 0. All of these off-diagonal terms are going to be 0. The surviving terms, the diagonal terms, well, it's not quite as good as before. This one is going to be -1 because The entire point of where we started picking the green vectors is that we started picking at the negatives. But at some point, we transition from being negatives to being zeros. So the last time that we're a negative vector is here, q plus k, I think that's what it's called for green. So this one is also -1. Okay, let's get all of this notation in order. And so just to be clear, we're then skipping a whole bunch of other stuff, and all of these are going to be 0 as well by the definition of k. So getting all of my sloppiness out of the way, that's going to be minus from this -1, the q plus 1 squared. And then every other thing is going to have a -1 in front of it as well, right up until q plus k squared. And then a bunch of zeros, which I just won't write down. And this is less than 0. Yeah, Goofy, thanks so much for coming by. So this is it. This is the end. The end. Okay. Why? Because we have, as was said earlier, we have this quantity VV, which is both negative. Did I get that one right? Negative, yes. And positive, or non-negative and non-positive, I guess I should say. Um, um, and to achieve, oh goodness, yeah, we're getting real sloppy with this lag. So let me start with the green one since it's the one that's currently on screen. So to achieve equality here, which we must, oh goodness, since this quantity has to be 0, so we have to have equality on the green side. But in order to get negative sum of squares is equal to 0, the only way to do that is to have each of the individual pieces be 0. Similarly, to achieve equality on the positive side, b1 is equal to b2 is all the way up to bp is equal to 0. So in other words, the relation is trivial, right? We had all of these coefficients. We didn't assume anything about the coefficients, but we have learned that in fact all of the coefficients are 0. I'm sure you can see the lag now. Good news is that we're done with the proof. um, I think what we should do is take another quick pause here. What I would like to do with the last little bit of time in the lecture is to, first of all, if there are any outstanding questions, feel free to say hello. Make yourself known. I'll do my best to address them when we come back. But I would like to give a slightly more informal, in the sense that I didn't write any notes on it, discussion the about the last remaining sections in chapter 7, which are this a little bit maybe about conics, and then a little bit about symplectic forms. Because there is a structure theorem. There's a structure theorem for well, not symplectic, but anti-symmetric. Or I'll get my notations right, but um, that we'll want to have going into chapter 8. So again, let's take a few minutes. Timing's not going to work out quite as cleanly here, but let's go for a 6-minute break. We'll come back at 35 after. So I would also like to uh, take a picture of this for our notes, and I will try to get these notes posted over to Simple Group. Simple Group server, which again, you can find that link over in the announcements message on the text chat for the event stage. Um, for now, let's take everything, start all over. So the last things that I would like to talk about are, we just finished talking, all of that material was from section 7.2. We're going to do a little skip ahead, since we have talked about a lot of the stuff in chapter 7 from our discussion from Freeburg. Thank you to everyone who was there. Anybody in the audience was a presenter that time? I don't think so. Um, the but so up next, quick chat about 7.6 and I believe 7.8. There's also a section 7.9, which I think we will not discuss here, since it's basically just a summary of what we had done. It's a really great summary. Artin sort of recognizes that there are all of these different forms going on with all these different properties, and it can be hard to keep this sort of stuff straight. If that's you, I would definitely recommend you to look at section 7.9. It's a pretty clean, simple summary of the major results. Okay, so probably most folks in here have seen the notion of a conic section before. You've definitely seen conic sections before, whether or not you call them that. Um, so, general, a conic. Here's hoping. Uh, well, a conic section is the Artin calls it the locus. So is the set. Goodness gracious. Oh, I just realized that is annoying, but it's only annoying to me. You can't see it on stream. Beautiful. Okay. Uh, um, something in the frame of my window is flashing. Set of points. X, Y, and R squared in the plane, such that we satisfy some b x or xy plus cy squared plus ex plus I don't know why I skipped d. D is a perfectly good letter. Plus f 0. Okay. Um, Artin writes this in slightly more algebra-y notation, which I will maybe resort to at some point. But so I say you've seen something like this before. Certainly, you've seen it in the setting where like e is 1, you know, b and c are 0. This is just a parabola, right? Y is equal to some quadratic in x. So this is just a general kind of setup there. It's called a conic section because it is a section of a cone. There's a very nice picture here that I will not say too much about, but um, can slice a double-sided cone in uh, with a plane and receive in return these precisely these kinds of shapes. Um, and so if you've seen anything about this before, you probably are aware of this sort of main theorem, which is that every conic section is either degenerate, in other words, it's linear essentially, or it contains only linear pieces rather than any like curved segments. This is not in general what the word degenerate means, but in this context, that's good enough. Or, and let me congruent to uh, the ellipse x squared plus y squared. Can I remember how to one? I'm just going to use the same notation that he does. And I guess I should be a little bit agnostic here about the like the relationship between these things, between these coefficients. I'm not claiming that that a is anything like this a or so on. Hyperbola a1 x squared minus a 2 y squared is equal to 1, or the parabola. And I think we can get away with a1 x squared plus a or minus x. So there are classification results. This is like a two-dimensional uh, object. There's classification results as you go higher and higher up in dimension. You have to understand what degeneracy means in that context. But um, these lists grow longer. It gets more annoying to do this kind of tabulation. But Arden talks a little bit about what the procedure is in general for doing this. I would like to say just a few words about the notation that like connects this to what we've been doing so far. Um, So we can write. Now I need to make a decision about whether I want to introduce this to or not. Um, I think I will not. So, the, or maybe I should say the expression of a conic is right. So this algebraic expression in the x's and the y's uh, can be written in matrix notation. Um, in which case it has the form uh, ax plus bx plus b. I think just a single number there. Where using the notation from above, x is equal to xy. A is equal to. This is where we have to be a little careful. I think it's A and C, but 1/2 B. B, and I guess let me just call that a capital C. B is equal to D and E, and C is just a number, which is F. And so the reason for doing this rewriting is that, hey, this looks familiar, right? This was our classic examples of bilinear forms. Hey, that's a bilinear form. I hand you a matrix, and then you put the, well, I guess it's not quite a bilinear form, right? Because what do I mean? Kinda? Ooh. Interesting. Well, sorry, I just ran out of recording space on my hard drive. So I'm gonna keep going. We're gonna finish this conversation, and if it doesn't get recorded, then I'll deal with that myself later. Um, so our bilinear forms from before were, things like BW is equal to M B transpose W. So this is like a bilinear form of this vector of variables, this vector of variables with itself. There's a much deeper collection of ideas here, a relation between so-called quadratic forms and bilinear forms as well. Artin is very intentionally skirting over discussing too much about this. Um, and so I will as well. But in particular, recognizing this allows us to take some of our tricks that we learned for writing linear forms, or excuse me, for writing bilinear forms in other bases and apply them to this situation. Uh, making linear change of variables to the x and the y uh, in order to produce a matrix that's better behaved, right? Probably diagonal would be nice. This corresponds geometrically to something very, very natural, right? In general, a conic section looks something like, I don't know, maybe if it's a parabola, it might look something like that. With the usual. And it would be nice if instead of working in, this black system of coordinates, we could work in this system of coordinates instead, so that it looked a lot more like parabolas that we're used to. Let me try drawing the symmetry axis first, and then something like that. And so indeed, the sketch of the proof for this classification theorem is that first find a better orthogonal basis. And better in this case means diagonalizes A. And then apply translations to clean up B and C. And so very briefly, to talk a little bit about part one here, and I will refer the this linear or this translation business to Artin, but so this this better when B exists by the spectral theorem. Okay, so remember what the spectral theorem says in our context. It says, well, we're in a real vector space, so the spectral theorem talks about for over R concerned with symmetric matrices. And indeed, A is a symmetric matrix, just by definition, right? The only thing we have to check is that these two off-diagonal entries are the same, and they are. So the spectral theorem applies, and what that means is that we have A is equal to P versus how do I want my thing to be? I would like it to be this way. Yeah. There. P. Not just for any kind of P, but crucially for an orthogonal matrix. Remember here, orthogonal means that P transpose, it's not self-adjoint, so it's not symmetric, so P transpose is not P, but it is P inverse. that kind of looks like I'm talking about symmetry. This is precisely what the spectral theorem says. For matrices over the real numbers, right? And I guess I should say D is diagonal to get the full power. Now, the fact that P transpose is equal to P inverse means that we can write A is equal to, just replace out that P inverse for a P transpose. And so by substituting that back into our expression from before, we have X transpose P transpose dP X, where A used to be, plus, as before, Bx plus C. And wouldn't you look at this, this, if you set y is equal to px, then this thing that occurs before here is p x transpose. So it precisely has the same form as it did before. Remember this business about multiply on the left by the transpose of an invertible matrix, multiply on the right by that matrix itself. Precisely what's happening with this. Is how you describe change of variables. And so then this we can rewrite, since P is invertible, certainly, this is equal to B E inverse times Y. Thus writing everything in terms of Y, and doing so in such a way that we've eliminated the off-diagonal terms of this matrix A. I didn't write down what I wanted to emphasize here, which is that is Y transpose. Right, so the new equation is Y transpose times some diagonal matrix, Y plus, let me call it B prime, some other linear term. It's a constant term. And that is why in this quadratic term, we don't see any cross terms. We don't see any x times y's. That's precisely why there are no such x times y terms way back up here in any of these conic sections, right? The parabola only has the x term. The ellipse and the hyperbola have both, but they don't have any cross terms. So Artin goes on to sort of finish this calculation, but the sort of, I think the thing that I want to highlight from this section is that there's this interplay. The spectral theorem allows this interplay between diagonalization, which is a concept that we're familiar with from ordinary linear algebra, like our first linear algebra course. We sort of finish that course usually with statements about eigenvectors and eigenvalues and diagonalizing matrices. But it connects that to this this stranger operation of multiplying not by P on the left, P inverse on the right, but by P on the left, P transpose on the right. Yes, that Viper. That is. Um, I've used the B prime notation for as shorthand for that matrix or for that vector. Sorry. And so, sorry, this weirder operation of multiplying by the transpose instead of by the inverse, that is a change of variables. And so what the spectral theorem does for us is it allows us a context in which changing variables is sort of precisely the same thing as this like conjugation action, this what you do for diagonalization. Um, Again, this the very last thing I'll say about this section is this blue equation that I gave, and in fact all of the work that I did down here, uh, as long as I modify this last line, works perfectly well over any higher dimensional vector space. Just define your vector of variables appropriately, your matrix of coefficients appropriately. Um, and so that allows you to perform the same kinds of classifications as we do with these conics for higher dimensional hypersurfaces, which are usually called quadric surfaces, or quadric hypersurfaces, I guess, in general. I really wish if anybody in the chat knows a good reference for this, I'd love to hear it. It's this is not a topic that I'm super familiar with myself, um, but it is one that I know it's very classical. People have thought about this for a long time, so I'm sure that somebody has written very lucidly about this. If you're interested in taking this further, um, yeah, if you'll allow me just a few more minutes, um, I want to write down the structure theorem for skew symmetric forms. It feels a little gratuitous. Um, Actually, no, no, I'm not going to do this. I will leave that to somebody who talks about the symplectic group when we get into chapter 8. Since it really is, it's just a page in Artin. If you've gotten this far in the book, you probably are not going to have too much trouble with that one page. Um, like I said, this was a little bit unscripted here at the end. Thanks so much for your patience. If there are further questions, either from this segment or from things we talked about earlier, this is a great time to ask.